So welcome back to the Q&A session. Today I will cover LTE, mainly LTE, the fourth generation of mobile communication system. So this is the last Q&A for this chapter 4, LTE, LTE Advanced, LTE Advanced Pro. So for LTE, I gave you some historical background, so it's not really not that long history. So it started, as you see, 2004, so 16 years ago. This is pretty young. It started only 10 years ago in Germany. So that's quite interesting to see how fast we can adopt such a technology. I gave you this example of the first cell here in Berlin, and what is quite important to see that LTE now basically takes over, well, the dominant role here in mobile communication system. 24, this is a projection. It's still the technology, and you see, there's something coming up. I will cover the 5th generation later, but to tell you right away, 5G is not a complete new technology. This is just an add-on to what we see today. So this is not groundbreaking new. This is not completely new. Whatever medium access as we saw when we went from UMTS to LTE. So LTE, this is why it's called long-term evolution, will stay here for a while, for the next, whatever, 10, 20, 30, 40 years. We will see. And this is one of the reasons why you see, there are only a few LTE not spots left on this planet, and all the other countries, they said, okay, we go for LTE. And I bet maybe this year or the coming year, you will see LTE in all countries. This does not mean full coverage. So I bet you will experience some problems here and maybe also in many places here and wherever. But okay, at least the operators in those countries decided, okay, let's start with LTE. Okay, I hope you had a look into the material. So if you think of LTE, why is it really such a worldwide success? We had all these problems with the 3rd generation. Oh, I want to have this technology or that technology. No, with LTE, well, almost everyone is adopting it. Okay, you mentioned you asked for North Korea. Well, I don't know. I bet they will adopt LTE pretty soon. And you're right that some of the virtual network operators, they do not always offer LTE. So it's indeed that not all. We have in Germany 3 operators, Telefonica, the Telecom and Vodafone, and only Telefonica offers typically for other providers, virtual providers, also full LTE support. Vodafone and Telecom also, but not always the same support they have for their own brands. So first they want to sell their own brands, and then they have some other sub-brands or also belonging to the big operators. We only have 3 real physical operators, but some of the virtual, they cannot always offer the same LTE service. So some of them do not offer LTE at all. Some now move to LTE, but limit the data rate. You're absolutely right. The reason is quite simple. So they are cheaper, but the networks are run by the 3 big operators, and they will not allow another virtual operator being cheaper and offering the same service. I mean, they would actually get all the customers from their own brand. And as you write, for example, yes, with some of the virtual operators, they fall back to one of the older technologies when you use, for example, a voice call. So voice over LTE is a special service not offered by all operators, not offered by all virtual operators. And to be able to use it, your phone has to support it. That's what all the new mobile phones can do, voice over LTE. That means voice over IP packets in the end. And But this is also a service differentiation between some of the virtual operators that are typically cheaper and the, let's say, real physical operators. So indeed, there are some limitations. So maybe limitations in maximum data rates, limitations in special services, or limitations sometimes coverage, or sometimes in which situation you can use which technology. You can also think of that some of the virtual operators have a maximum capacity and the real network operators will kick them out of some cells if they are overloaded with their own customers. So yes, there is a reason for, or at least they will tell you there's a reason for paying more. If there's really a reason, well, you have to decide on your own. But usually if you compare what you have to pay, typically you pay a bit more for the real, let's say the physical network operators, and the virtual operators are cheaper. And there are many reasons for this. Sometimes the service, sometimes there is no hotline. Well, there is a hotline, but unreachable, or whatever. They don't have any real stores, etc., etc. So there are many reasons. Okay, but back to the question. So LTE is a worldwide success, not yet in 3 or 4 or 5 countries, but we'll see what the future brings. But what are the reasons? So why is it such a tremendous success? Why is everyone now going to LTE? Flexibility, exactly. That's one of the reasons. So if you think of the frequencies, and that's just a part of the bands where LTE is operating. So depending on the country, we can use different bands, and you see so many different frequencies. And that's not all. There are even more bands. This figure doesn't show everything. So many different frequencies. It can work in a paired band or unpaired band, so FDD and TDD. It can use many different modulation schemes, and this makes it quite attractive. So as soon as there's spectrum available, you can squeeze in LTE. And this is because you can operate with many different, and this is the initial release, with many different bandwidths, 1.4 up to 20 megahertz. So for low data rates, for higher data rates, you can operate it at 700 as well as 2700 megahertz. You can also operate it at 400, but this is just an example for the initial release. So very flexible. The second part indeed is it has a much simpler architecture. We'll come back to the architecture in the next section, but the architecture itself is very simple. And from a very high level view, maybe you remember, well, this is pretty much the same we already have in UMTS. It's pretty much the same we have in GSM, the core architecture from a high level view. But yes, sure, we changed the radio interface. This is now the LTE UU and not the UMTS version. So as you learned, we have no CDMA anymore. Okay, but what is furthermore quite important, Evolved Packet Core. That was our old core network. This is now packet switched only. So only packet switching. This is much simpler. We do not have this circuit switching anymore. We have only packet switching. There are pros and cons for that. So the advantages are you use routers, you use more or less internet components. We know how to operate this. We know everything about the flexibility of this packet switching architecture. So we don't have this setting up connections and all these issues. The disadvantage is, well, what about quality of service? How to guarantee this? So there are some additional mechanisms needed, but it makes the whole architecture much simpler. So that is a big advantage, and especially if you look inside the architecture, I will also later come back to this. If you look at the core, you see there are very few components. Basically, you have routers and you have some management entities. So only two different main components. So the MMEs, the management entities, and the routers. And that's it. So there's no circuit switching part and packet switching part. So if you have more different elements, this means maintenance, updating, hardware, etc., etc. So that is quite important. And as you write, this is exactly correct. Without the circuit switching, only relying on packet switching, we don't care how this IP packet reaches the UE. So, not shown here, you can also have a connection to a wireless LAN. So, this is what some of the operators offer, that they can offload a part of the traffic to available wireless LANs. Yes, there are some conditions, so you have to be able to use the wireless LAN, etc., etc. But LTE can also use this unlicensed technology. So wireless LAN technology is also usable. So you can combine this, which is quite nice, because sometimes you have a hotspot available and you're in the middle of the call, and if you move out, depending on the support by the operator, the system switches then over to LTE. And this, as this is all packet oriented, well, then the packet flow is basically rerouted. So that's the whole idea. So the flexibility is higher and you can integrate different technology into this. So I remember there were also some experiments in 3G systems, how you can switch back and forth from wireless LANs to 3G, and this was also available, but now it's much simpler. If everything is packet switched, it's just a question of rerouting. Well, just a question. Okay, you have to do this fast enough, and you have to provide the packets right in time, otherwise you will have a service interruption. Especially for voice over IP, you will notice this. But you're right, so no matter how this IP packet reaches the mobile station or the user equipment, well, the user equipment has to support this, but this is one of the ideas. Okay, so that's the flexibility, indeed. Okay, frequencies and parameter. So if you compare the networks, well, we almost talked a bit about this. There are some differences. Now, especially if you look at LTE and the third generation, so the differences here, main differences, if you think of from a high-level perspective, so what are the main differences? So the internal architecture looks pretty similar, or not. The core is different. Well, as we just said, circuit switching is missing. So what is left is the packet switching, which is not identical, but that was the idea introduced here, the GPRS that introduced the packet switching. What else is different? So if you, okay. So here in UMTS, we use CDMA. That was the technology industry decided for in 2000, said, okay, let's go for CDMA. I told you about the patent wars and all these problems. And now here for LTE, we are back at frequency division multiplexing, and also the access based on this, and time division multiplexes. So it's a mixture. So basically we dropped the whole code multiplexing. So we dropped part of the core. We dropped a technology that's today considered as sometimes too complex. So all this power control, 1500 times per second, that wastes energy, that's complex. And that's a problem. But as you write, that's correct. Here we can do our soft handovers. That's what we learned, because we can have a connection at the same time to different base stations. And here we are back at a hard handover, but okay, this is a hard handover when you really look at the connection between a user equipment and a base station, because this is defined by certain time frequency slots. I will come back to this in a minute. And but it's not the same hard handover compared to GSM, for example, because now we're talking about packets, data packets. So yes, it's hard when it comes to frequency, so we cannot have a connection to several base stations simultaneously, but it's not a hard handover compared to GSM, where you have this connection and where you have to switch over the connection controlled by, for example, the mobile service switching center and the base station controller, etc. Here, yes, it is hard, but, and this is what we cover in the next section, but you can make it a bit, let's say, softer in a way that if you think of, okay, there's one antenna and there's another antenna, and here's your user equipment, and you're connected to this, and now you switch over to the other one. The Evolved Packet Core you can already provide, and also the Evolved-UTRAN. So this is the UTRAN. Those components, they can provide the packets not only to the currently active station, but also to the new base station. So that if you hand over, the new packets are already there. So this is when called, for example, a seamless handover. So you will not notice it in terms of, okay, the packets are delayed. Because maybe you remember from our computer networks course that if you operate on IP, well, basically you cannot really guarantee that much. So packets may be delayed or reordered or whatever. So here, to make this handover a bit more seamless, you can already provide data packets before the user equipment switches over with a hard handover to a new base station. So that is the idea. I will come back to this seamless and lossless handover also in some of the following slides. Okay, so there are some differences, but you see they also have some parts of the architecture in common. It's quite clear that we do not have the same hardware any longer, because GSM now, that's really too old, because the data rates are way higher, etc., etc. But it's just the way of how the architecture is, structured. And also this makes it easier to go from one architecture to another one. If you just say, okay, we can drop a part, but we can stay with some of the parts, and then we do some updates, upgrades, etc. of hardware and of software. Then LTE offers something new that's called the soft frequency reuse. What is the idea of soft frequency reuse? Remember, we are now at FDMA, TDMA. Again, no more code multiplexing. So what was the idea of this reusing of frequencies? Any ideas? So soft frequency, more bandwidth next to the cell. Right, that's one of the big advantages. Soft frequency reuse. The key idea is as follows, also shown on slide 114, but I can also explain it here. Think of this is one of our cell towers. That's another one. And they typically create their cells, and the cells are overlapping. That's the normal situation you have in a cellular system. And we learned in the context of GSM and also in the earlier chapters that in neighboring cells you cannot use the same frequencies because then you have interference. So you have one frequency in this cell, another frequency in this cell, and in the overlapping regions, doesn't matter, you have different frequencies. Now the idea is we do not use all the channels, so all the bandwidth, the part of the spectrum we have in a cell with full power, but we use a part of the spectrum only with less power. So we restrict the cell size for certain frequencies, and now these frequencies can be reused because they do not overlap. So we can reuse for all the cells with less transmission power the same part of the spectrum. No overlapping, no interference. And only for a minor part of the spectrum we send with more power. This part of the spectrum will then overlap, and for these frequencies we have to use different frequencies in the cell. So that is the idea, that you can reuse, and this is why it's called a soft reuse, because you can dynamically adjust which part of the frequencies you send only with less power or with more power. And so you can reuse the same frequencies here for the mobiles closer to the BTSs without interference. So we do not have this strict hexagon pattern we had for GSM, for example. So that is the idea here, that we say, okay, we reuse part of the frequency. So slide 114 shows this with color. Okay, so no more code multiplexing. In code multiplexing, you remember we all used exactly the same frequencies. So one operator had 2 times 5 megahertz, for example, and all the mobiles operate there, and we separate it by code. Here we separate in time and frequency. So this is one of the differences. Okay. Well, in the next section, I covered the architecture, and especially, so besides the architecture, so the architecture I showed already here a bit, that was exactly this more flat structure where you have for the data transmission only the routers. So you have to distinguish the solid lines. This is where the data flows, and the dotted or dashed lines, this is where the signaling goes. So the control data, controlling mobility, for example, controlling the different nodes. So it's a way simpler architecture. That was one of the points. And also you see the LTE-UTRAN. This is now the evolved radio access network, and now it's the evolved UMTS, terrestrial radio access network. It was called universal and they switched back to UMTS, but okay, LTE-UTRAN is also simpler, as you can see, because there are only the 2 components are the eNode Bs, the involved node Bs, and the user equipment. So no more separate controllers, whatever. And you see that the eNode Bs can create a meshed network. And you also see that eNode B can be controlled by several control units. So it's flexible, and this shows only one way of connecting these elements. So the architecture and the standard is quite flexible. So you can think of any kind of partially meshed topology, so depending on the purpose, redundancy, robustness, etc. So this was one of the points. And then I also introduced what is special about LTE, and this is very, very simplified. The key idea is that, as I said, we drop the code multiplexing, but we multiplex in time. So this is time division multiplexing in this direction. And we multiplex in frequency. So that is our frequency division multiplexing. And the key idea is that we basically give a certain user equipment certain part of the spectrum, so several channels. Here it's 180 kilohertz. So we actually create this part of the spectrum, assign this to a device for a certain amount of time. So here simplified 180 kilohertz for 1 millisecond. If you look into the standard, if you follow some of the links, you will see it is indeed way more complex. That's the basic principle, but you can do within such a so-called resource block, you can do a lot more. But that's the key idea, that you have these resource blocks and that the base station, your base station, the eNode B, then decides which user equipment gets which part of the spectrum at what time slot. And this is how you can very flexible assign resources to different devices. And one of your questions is, why does the user equipment 1 has so much, resources? Well, think of maybe the UE1 wants to transmit a video of high data rate. Then you assign more resources to this one. And then other user equipments maybe just browse a web page or just send some messages or whatever. Then you can assign less resources to the other devices. So you're very, very flexible. And additionally, you can assign the different parts of the spectrum, to a user equipment. So another question is, why do we see a user equipment on different frequencies? So first of all, again, this is simplified. So the idea there is that you can give away available resource blocks and you can dynamically assign resource blocks. So this is 180 kilohertz within 1 millisecond. And no matter where they are, so you just assign resource blocks. And if you have certain gaps, you can use these gaps and say, okay, this resource block is for this and that user equipment. And as you're using OFDMA, orthogonal frequency division multiple access, so that means you subdivide these resource blocks in many, many, many small so-called carriers. You assign, a selection of the carriers to your data stream. So your user equipment, for example, the mobile phone, sends the data stream, and then you do something. You can look this up in the standard. This OFDMA, orthogonal frequency division multiple access. We covered this briefly because this really goes deep into electrical engineering and signal transmission. And with the help of this, you can distribute this data over many, many, many small channels operating at certain carrier frequencies, orthogonal carrier frequencies. So this was this picture when I showed you have many of these channels close to each other. And basically this is, similar to what a DSL router does, using many different frequencies. You split up your data stream to these many frequencies. And the trick how you can do this is with the help of Fourier transform, fast Fourier transform and inverse fast Fourier transform, FFT. And this helps you basically splitting your data stream onto many different carrier frequencies. And the chips then can select the appropriate carriers, create a signal that occupies a certain part of the spectrum. So, and this then in the end depends on how you assign which part of these resource blocks to which of the devices. This picture is simplified because there are many things missing. If you look this up in the standard or in some of the real LTE tutorials, you will find, oh, you need many pilot tones and you need synchronization and you need many, many more things. So there's a lot more done. This is just the basic principle that we now separate in time and frequency the different data streams from different user equipments. You can also send with different signal strengths in these resource blocks, etc., etc. So this should just symbolize in a way that you are now very, very flexible in time and in frequency. And everything that goes into more detail, well, we would have to learn a lot more about how we create signals, how this is done, how we split our data stream onto different carriers, etc. This would actually lead us away from the more computer science part of this. Okay, so but that's the basic principle. And so as we are doing this, as we use again time slots and frequency to separate, we run into all these issues I explained, like time alignment, because we have time slots again, so we have to do this, and the issues of where I just explained, we have a handover. So we have something that is a hard handover exactly here. Once more, you don't have to learn this type of figures. This is just to explain the different behavior and why we have a hard handover. So you switch here between these two steps. Your user equipment switches from the source eNode B, that's here, to the target eNode B, that's here. So this is a hard handover, but we can already provide packets at the target eNode B. And that was exactly explained here, that also here we perform a hard handover here, because we hand over from the source to the target eNode B, but we can already provide data at the target eNode B to, well, avoid data loss. So just think of, we have packet switching, so we can send, this is your normal way, this is your packet flow, and if you know that you will perform a handover, well, the network knows, then it can also duplicate the packets and send them this way. The devices know how to handle duplicated packets. The big advantage is that the packets are already there when you arrive at the new eNode B. And there were two different modes. There's a lossless handover. Lossless, that means that in case you moved away from one of the eNode Bs and there are still packets arriving for this user equipment, the eNode B will forward the packets to the new one, so that you definitely will not lose any data. But maybe these packets are late. I mean, you can imagine you switch from one eNode B to another one, there are still packets arriving. The lossless handover only makes sure that you will not lose any packets. Or there's the version of the seamless handover, and for the seamless handover, that means you copy the packets. So before you switch over. So there are different ways of providing already the data packets at the target eNode B. And to make this faster, you have this connection between these two eNodes, the eNode Bs. Okay, so you have another question before we come to my question. You asked that the radius is just a theoretical maximum based on the timing. Yes. So that's just the limit because of this time alignment. So similar to GSM, the 35 kilometers. So yes, you could think of an LTE transmission, whatever high power transmission, so that the signal's still strong enough. But to be honest, at 100 kilometers with normal devices, you will have a problem. I doubt that your mobile phone will really cover 100 kilometer distance. It's not only the base station, it's also your mobile phone has to be able to bridge this. So that transmission power is a problem. So this is maybe in most situations just a theoretical limit, because 100 kilometers is quite wrong. So maybe over the ocean, when there are no obstacles and nothing in between, no hills, maybe it might work, but 100 kilometers is quite a long way. So usually you have less than, I don't know, a kilometer, something like this. So you have many of these base stations, and you even have the picocells and the femtocells and whatever. So you have in lamp poles and in whatever, in many shops and shopping malls, you have LTE antennas. So the distance is not, well, usually just some 100 meters, up to a kilometer, but not 100. Maybe on the countryside you reach something like 30 kilometers, but 100, whoa. But yes, so there's the theoretical limit, because then you cannot align the data any longer. And the alignment is important for the packets you send towards your base station, so the eNode B, because there they have to be synced with the time slot structure. Otherwise you have the usual problems of overlapping data. Okay, so that is the basic idea here. So if you look at the architecture, we covered this already. I'd say if you look at the architecture, you said this already, we dropped the circuit switching part, we kept the packet switching part, and yes, not only new acronyms, also a bit new functions. But in the end, if you look at the core, this is our packet switching plus something like our this is something like a home location register, because this is exactly where you have the subscriber information. So maybe roaming restriction, allowed packet data networks, your maximum data rates, all these things. Plus, you know the identity of the MME for the current location. So that again is a kind of a tracking area, a larger area, so you know roughly where someone is. So that's the idea. Well, the operator knows precisely based on the cell, because all our devices are always on. Okay. And then we have the authentication center also there. So you see this is something like the HLR basically. Okay, and then some additional functions, and I already said, so the difference here is it's simplified. So we don't have separate RNCs any longer, so this is now all integrated. That's the core idea. Okay, so these are, by the way, just some typical questions also for exams that I might ask. So compare this with that. Then there's not the own single correct answer, but this is rather a comparison that you see, okay, advantages, disadvantages. So if you compare what is new, what stayed more or less the same. So that's the point. Okay, so I noticed that I explained already some of the questions while explaining again the technology. So there's this new connection X2 between the eNode Bs. I talked a bit about seamless lossless handover, and this is what you can use these X2 connections for. But what else can you imagine? What can you use the X2, these connections between the eNode Bs as well? So what is the advantage of having these? So I mentioned, okay, you can, for seamless handover, already forward packets here. But what else could you do? Could you think of a scenario where these connections might be helpful? Handovers without the packet core, yes. Safety, if a node B fails. So that's basically you introduce redundant paths. So imagine someone, now assuming this is a wire, cuts the wire, or something happens with a link between eNode Bs. So then you can reroute traffic. It is routing, so we know from the internet how routing works. So you can reroute traffic. So that's right. So we have increased redundancy. That makes the network more robust against failures. So that's one thing. And there's something else, this relaying. So not all eNode Bs need a direct connection to the core. So you can set up a network or make the network denser, better coverage, higher capacity by creating a new cell. And if you notice, oh, there's still a white spot, then you create yet another cell here, and you just combine or connect these eNode Bs with a new eNode B. You do not necessarily need a connection to the packet core. So you can actually create a way more flexible radio access network. That is one of the ideas. And then you mentioned also, that's absolutely right, what happens if we do not have any connectivity anymore. So we could also think of an kind of an, well, not really independent, but a radio access network that could operate without the core. I don't think that the operators here can really do this, but in theory you could do this. You could even directly communicate between two user equipments without the involvement of the network at all. So this is called device-to-device communication. So you see there are some features, at least in the standards, that create a not only flexible but way more robust network. And this was one of the ideas that where you say, okay, maybe now we could use the network on certain frequencies also for firefighters, police, etc. Because we do not necessarily rely on the whole network. There are some elements in LTE that support this ad hoc operation, this kind of without infrastructure operation, and even device to device without the involvement of a eNode B. And this is indeed, you asked, is this was LTE Advanced and Advanced Pro does? Yes and no. So Advanced and Advanced Pro, I will cover this in a second, is mainly about higher data rates, but you're right, the new releases of 3GPP that cover the higher data rates also describe the device-to-device communication. This does not mean that your mobile phone supports this, but the standard supports the device-to-device. So I think that maybe the operators don't like the idea because device-to-device means no money. So if you don't need the network, this is rather this walkie-talkie functionality. But indeed, this comes with the newer releases, the device-to-device. I don't know exactly, release 14 or so. This is where you have these functions integrated. So indeed, we are way more flexible also in these terms, which is good. So seamless, lossless handover, this is exactly, we duplicate packets. We can do this in many different ways. And this is what I explained, because we do not have this circuit switched idea with connections, we have packets. The eNode Bs can duplicate the packets. I mean, you can think of duplicating wherever you want and already send the packets to the target eNode B, that as soon as you arrive there, the packets are already there. Or if there are still packets arriving at the old eNode B, the old eNode B can forward this packet to the new one. This, by the way, is exactly what is done in mobile IP. So this is basically the same. I will cover this in the chapter after wireless LANs. So mobile IP, this is where you have mobility support on layer 3, internet, IP packets and mobility support. And this is exactly what you do here. So you will learn how this works when we come to mobile IP. So it's interesting to see how these mechanisms now are introduced in these big mobile phone systems. Okay, now something special compared to the internet. How can we now at least guarantee from an LTE perspective, when it comes especially to the radio link, how can we guarantee data rates? How can we guarantee certain delays? Well, this is pretty simple. Exactly, you assign resource blocks in a kind of a static fashion. So every 10th resource block or whatever kind of frequency. So if you need higher data rates, okay, you assign more of the spectrum. If you need a certain maximum delay, you have just to make sure in the scheduler, in the eNode B, that you assign, well, in a periodic fashion, the resource blocks. That's the core idea. And if you at the end look at the multiplexing and multiple access schemes and compare LTE, UMTS, GSM, differences, similarities, I guess we covered this already. This is exactly that we are now back at a scheme that is not like in GSM, not at all. There we had our data slots and circuit switching, but now we add a flexible way of using the frequencies, and this is only possible because we use this OFDM technology. So, but again, this goes deep into electrical engineering to explain the details of this. For here, it's enough to know, okay, we can dynamically assign parts of the spectrum for a certain amount of time. And this is then used for the multiplexing of different data streams, different users. And we can also use different sending powers to different users, etc. So the base station will send different resource blocks with different signal strengths to different users. And this is also how we do this soft frequency reuse. So not all the frequencies are sent out with the same power. So we have only the major part with less power, this kind of inner cell, and only some of the frequencies really use the high power to reach the user equipments that are somewhere out there in the cell, in the overlapping area, overlapping with other cells. Okay, so I guess we covered this. But if you do have questions, just ask. And you see from the slides, this is really higher level, and even with this high level, we do not go into all this ping-ponging of handover, etc. details. This just should give you an impression of what is done right now. And then over the last 2-3 years, we saw the real 4G systems, so LTE Advanced, that is our real 4G system. LTE is not really 4G, and then the LTE Advanced Pro, that is, let's say, 4.5G, and this is mainly about higher data rates. That is quite important, but also, and this is what I mentioned, public safety features, the device-to-device communication, and also machine type communication, because the engineers noticed that, and also the operators, that yes, we have many people talking to each other, downloading something, but we have many more machines. And this is why now we also have this machine type communications. Okay, there was some more questions about the soft frequency reuse. Is this done dynamically, automatically, or does the operator need to assign this manually? So this is usually done fully automatically. So the operator might set certain goals, plans the cells. So the operator is responsible for cell planning. But the systems can do automatic load balancing because you do not know in advance the precise load. So this is why this load balancing between cells and how much of the spectrum you use, etc., this is done automatically. So yes, I guess you can set certain goals, certain limits. So for example, you have to keep a minimum capacity in each cell, etc. But it was similar in GSM when you borrowed channels from neighboring cells. This is done automatically. So, okay. So, and the network itself, and this is a good question with this, is it done automatically? Sometimes the LTE network, the core, is also called a self-organizing network. Self-organizing because the idea is that you place the components somewhere and then the network organizes itself. When it comes to routing, when it comes to frequency use, when it comes to sending power, etc. So it's self-organizing, and this helps setting up the network. Also, after some, for example, earthquake or whatever, the idea is that you can very quickly reinstall such a network, and the core components will configure itself. So from a high-level perspective, this is similar to an IP network. We have the routing functionality, we have the routers, we somehow plug them together, and then the routing, OSPF, etc. does the job. So that's the basic idea. So here LTE Advanced, Advanced Pro is not only about higher data rates, I also showed examples of lower data rates. So higher data rates was going to the left. So you have more and more gigabits and using more and more of the spectrum. But if you go to the right, you use only, let's say, 200 kilohertz and only some kilobit per second. This is the narrowband IoT standard in LTE, coming with releases 13, 14, etc. So that was also the idea. So these are the two directions of the newer versions of LTE. And you had the question about, do we reuse internet protocols like BGP, etc.? Yes. So in the end, the operators can use whatever they want internally inside their networks. But as soon as you're connected to the internet, so the connection to the outside world, then you're exactly in this family of internet protocols with BGP, the Border Gateway Protocol, connecting different autonomous systems. So then you have your mobile phone network for a certain operator. This could be an autonomous system connecting via a border router to other packet data networks. Well, usually the internet. So you have your whatever LTE network, and there's somewhere the router, that's our gateway. And this router then talks to, it's always at the packet data network. Well, in reality, that's, you could say that's, for example, the internet, and not only the internet. So you can connect this network, for example, to some peering point, a peering point where you exchange traffic, which then connects to, let's say, thousands of other autonomous systems. So these are autonomous systems. So these are backbone networks, our research network in Germany, or whatever. So this could be a setting. And this is exactly between the autonomous systems. So you can also connect here and connect there. So you can have many connections, not only the peering points. And here you use the BGP, the Border Gateway Protocol. It's about the border gateway. So the routers at the border, they use the BGP to talk to each other. Inside the networks, okay, this is now from computer networks, you use usually protocols like OSPF, a routing protocol, and that's something you can use here. You can come up with whatever routing protocol. So as soon as you have routers, you have to find a way through your network, and then you can use such protocols. You can use whatever you want, but this is one of the classical internet protocols. What the operators use, well, you have to ask the operators. But this is classical internet technology, and that's one of the ideas, that in the end we do not really distinguish between, oh, now this is the core of a whatever mobile phone network, or this is just whatever a routed internet part of the internet, an autonomous system. Yes, we do have the additional mobility functions, the policy functions, so quality of service support. So this is a difference from the internet. So this is not the normal internet. In the normal internet, you don't have this mobility support. You cannot guarantee certain quality of service, etc. So there are differences. But so BGP can be used here to connect to other networks, not internally. So okay, now you saw the LTE, the classical LTE standards, the Advanced Pro, but also the versions for the Internet of Things, these standards. And so now what is evolutionary in this LTE? And how do we see the different demands reflected in LTE? When you look at LTE and you look at the different applications, how are the applications then reflected in the standard? For example, if you think of Internet of Things, something like this. Here you see quite nicely how the different applications influence the standard. Yes, for example, sleeping, fast data transfer. So some applications need long sleep periods. This is supported by narrowband LTE, that you have extended sleep periods. So, and LTE can support this kind of narrow band use. So you can replace single channels of GSM. That's one of the ideas. But some applications need high data rates. This can also be done in LTE. So LTE is extremely scalable. Scalable when it comes to data rates, and this is reflected then also in the spectrum use. So you can start with 200 kilohertz, 1.4 megahertz, but also whatever, n times 20 megahertz, depending on the available spectrum. So LTE can be adapted. And this is also one of the reasons why many people think, well, LTE, this core technology, will take over many of the other or several of the other standards for these applications. So for example, when we talk about wireless LANs, we will see that, okay, why not using LTE for a campus network? Okay, we have operators, maybe we don't like one of the three operators here in Germany, but why not setting up your own LTE network or whatever? So this is things people think of, because you can use many different frequencies, many different cell sizes, etc. Also, Internet of Things, we'll hear a bit about ultra-low power technologies, but you also have this narrowband IoT technology. So there are operators offering narrowband IoT access. So many of the base stations offer this. So this can be used for the Internet of Things. Still, there might be devices that are ultra low power, and then this is still too much power required here. But it shows that LTE is quite flexible. And the funny thing is that if you look at the, well, in the next chapter, at the absolutely newest standard for wireless LANs, .11ax, you will find LTE technology in there. So that's quite interesting. We'll cover this in the next chapter. So the evolutionary, well, let's say the different applications are reflected in different spectrum use, sleep patterns, data rates, different frequencies. So sometimes, for example, for smart meters, you have to penetrate walls to get down to the basement where your electricity smart meters are, water meters are. So then with LTE, we can use lower frequencies. So it's quite flexible. So LTE does not say, okay, you have to use exactly this frequency or exactly this bandwidth. So it's more flexible. And then there was also the question, what is evolutionary in LTE? Because it's called long-term evolution. Well, in the end, exactly this is what I said. So, oh, there's a new demand. There's a new application. So let's scale down. So in the early days of LTE, we started here, category 1 devices, and then going to higher data rates. And then suddenly IoT showed up, Internet of Things. Okay, now let's scale it down. So that's the evolutionary part. So it's not a revolution coming up with a complete new medium access scheme just because we have IoT. No, it's rather we integrate it into LTE. You need device to device? Okay, then we integrate this. And this is why maybe for marketing reasons people talk about the 5th generation, but you will not really see a clear cut between the 4th and the 5th generation, because you see the LTE technology now using higher frequencies, for example, millimeter waves, so 60 gigahertz, something like this. There's also a new radio, okay, new modulation, yes, but why changing the core? The core itself, it's flexible, it's packet oriented. So that is the core idea of this LTE. So in the end, if you're interested, look this up at 3GPP, and there you will see, okay, everyone is talking about 5G, but it's not this clear cut that you see, okay, now they use this whatever fancy access scheme or whatever thing. You will see, oh, higher modulation schemes and a bit more here, a bit more there, but not really completely different from what we already have. So that is the big advantage of using this relatively simple packet switching plus some more, let's say, quality of service components that you can guarantee at least a bit. Okay, so that was basically all about LTE. And if you have questions, please go ahead and ask. Not that I know everything about LTE, but maybe I can answer some of the things. And you see that this frequency stuff is still going on. I think in Germany 2015 we had an auction for some of the frequencies, and we are now using, I think that was exactly when we dropped the old digital TV and now using DVB-T2. This is where we use LTE at 700, at about around 800 megahertz. And we also use it at 2.5 up to 2.7 gigahertz. So that's also. So what happens in the next 3 to 5 years for mobile communications? So to be honest, the normal user will not see that much from 5G. So we will have maybe a bit higher data rates. But in the end, what is offered right now is enough for the typical human user. That means you can already transmit 4K 60 frames per second. And if you can do this, fine. You cannot receive with your human eye more. That changes as soon as you integrate something like the tactile internet. So if you touch a surface, it will immediately respond. And this together with augmented reality. So you have your augmented reality classes, whatever, like HoloLens, something like this. And you touch something and you get an immediate feedback. This requires not higher data rates, but ultra low delay. So the trend right now is not more gigabit per second. So in terms of gigabit per second, I think LTE Advanced Pro, that's quite a lot. I mean, there you have a lot. Okay, coverage, that's a different story. I mean, I don't talk about coverage. That's definitely something that will happen. So we'll have much better coverage in the future. But the peak data rates you see here, depending, so you will see something like a gigabit per second. That's enough. But what you will see in the next 3 to 5 years are dropping delays when we go to the new radios. So a low delay is extremely important when we talk about this tactile internet. So that's just a keyword, buzzword, right? You can look this up, tactile internet. So you touch something and you get an immediate response. That means within, let's say, 10 milliseconds. That's like touching a surface and you get a response from the surface. And this is where you need this really low delays. That's just one application for ultra low delays. And we will see lower delays. So delays that are less than 10 milliseconds, better around 5 milliseconds, and therefore we need something that's called ultra reliable low latency communication. But here we are in the field of research. So what I explained so far are products out there, standards and products. But if you really want to have this ultra reliable and low latency, then this is for, let's say, autonomous whatever. So autonomous cars, autonomous robots, whatever, ultra reliable and low latency. And this is extremely complicated because reliability is usually achieved via retransmission. But retransmission consumes too much time. So yes, forward error correction, etc. and low latency, that's a problem because coding costs time. So that's really a problem. So ultra reliable and something like 1, 2, 3 milliseconds delay. That's a problem. So, but this is what we will see. So not that much in the normal consumer markets so far. So the normal smartphone, yes, will have gigabit download, fine. You can watch movies, great. But what else? Right now with the devices, what else could you do? But as soon as you have this kind of VR or AR, so virtual reality, augmented reality headsets, then you need exactly these high data rates to have a nice virtual reality or augmented reality and ultra low delay. I don't know if you ever used VR or AR headsets. If you have an increase in delay, you really get sick. You cannot use this. I mean, if you turn your head and then it takes a while until the environment adapts, it's a nightmare. So delay is a problem, and delay jitter, so variations in the delay, and this is what industry is working on. So this is what I will briefly cover in the 5G section. But 3 to 5 years was the question. I doubt that you will already see complete, let's say, networks plus chipsets, plus devices, plus good applications. Let's rather talk about 5 to 10 years. Because yes, in a lab environment, yes, but think of a normal city and you're walking around with your AR glasses and you, let's say, walk through Berlin and want to see some explanations about something and you want to touch some virtual surface, etc. This takes some time before you install all this. But that's extremely important. So you're right, the motion sickness is a problem for virtual reality, but also on AR you will not get sick, but it's annoying. So the real world is stable because you're looking through the glass, but if the virtual world doesn't really follow, or you touch something virtual and this is somehow detached from the real thing, so the idea is that you grab something, but you project a certain surface on this something, maybe a fur on a ball, on a plastic ball, and you touch it and you want really get this fur feeling or whatever surface it is, and then you really need these low delays. Otherwise, it's not the perfect feeling, because as humans we are used to, you touch something and it feels like plastic, like rubber, like metal, like whatever. So we will see, but at least it's interesting. And you're right, with a real VR environment, it's a problem. AR, at least you see the real environment, which has no big delay, so speed of light, but that's not a problem. Okay. So that's one of the things. Then whatever ultra high density, whatever we will see high density. So high density when it comes to Internet of Things, today we have per square kilometer, I don't know, let's say 1,000 users. But if we equip everything with internet connectivity, so not only cars, but buildings, a door, whatever, street light, etc., we have tens of thousands of devices in a certain area. So high density, that's also always an issue, and there are certain upper limits today, so that's something. Okay, so VR, we covered this. AR. So other questions. So AR solved by Tilt 5. That's a bit off topic. So if you're interested in AR, yes, look up these hints. I'm only talking about the communication part. So this was, I think, was it 10 years ago when this tactile internet stuff came up? And I said, okay, can't I touch something and get immediate response? And immediate means less than 10 milliseconds or 5 milliseconds or whatever. This puts a lot of pressure to the network. So this is where you need something like edge computing. So that's something we will see more and more, that data will not necessarily go to the operator, but will be stored and computed, whatever, at the edge, so closer to the customer to reduce the delay. So the gray boxes at the curb down there in the street, they are not then stupid, or not that stupid, DSLAMs, so DSL access multiplexes, but they could also store, let's say, 1,000 or more of the brand new video clips, movies, etc. And if you, with your mobile phone, just move by and want to download, you will download directly from this gray box, from the edge of the network, and not from some content provider somewhere deep inside the network. So that also lowers the delays. Because what's the use of tens of megabits or a gigabit on your mobile phone if you still have the delay if you click on something? So that's the idea. That's another buzzword. It's called edge computing. So after the cloud, which is already a cloudy term, after cloud, we now operate at the edge of the network. So we do more and more at the edge. Okay, there was another question. Do using higher frequency means higher discharge of battery? So using higher frequencies, well, not necessarily means you, well, need more energy, because using higher frequencies, you typically have higher data rates, which means you have to send only a fraction of time. And energy, that means, well, you're sending for a certain amount of time with a certain output power. And if you send for less time, you also need less output power. Maybe stronger, but less time. So it's a trade-off. So there's a so-called ultra-wideband technology where you send only a very, very short, some nanoseconds, which spreads your signal over the whole spectrum with high energy, but just some nanoseconds. And this saves a lot of energy, although you create quite high frequencies. So this is not really the reason. The real reason is IoT uses lower frequencies because you want to penetrate walls, concrete, whatever, trees. That's one of the reasons. And also, depending on the technology you use, it's simpler to create the electronic circuits. So today we know how to build 2.4, whatever, 5 gigahertz. But for millimeter wave, 60 gigahertz and IoT, you will run into problems. But still, feasible, everything is feasible. But the main reason is really penetration of walls, because IoT, the things, they are somewhere hidden, installed in smart buildings, or used somewhere to control machines in basements or somewhere in buildings or in cars or whatever. And then you run into problems with high frequencies because the attenuation is already quite strong at, let's say, 2 gigahertz, 2.5 gigahertz, the ISM bands. you notice at home with your wireless LAN, as soon as there's a wall, you run into problems. So that's the main reason. Plus, for many of the IoT devices, you have to use license-free bands. So you cannot just say, oh, I like whatever 2.6 gigahertz. No, you have to use one of the license-free bands. And this is why we are stuck to 433, 868 megahertz, for example. These are typical license-free bands where we can operate the devices. And then the range indeed is much higher at low frequencies. So if you think of LoRa, long range, this wireless technology, you can cover several kilometers with relatively low energy because you also use low frequencies. Okay, then next special question. Is it a good idea for IoT to sleep and send rare data via message queue or MQTT protocol via Wi-Fi, or is LTE better for the battery? Well, that's a good question. Okay, to be honest, it typically depends on the concrete technology. So if you have a stupid LTE implementation, the hardware, a stupid hardware, and very good Wi-Fi, then Wi-Fi is better and vice versa. So in the end, it depends what was the original purpose of technology. So Wi-Fi, the original Wi-Fi, was not made for really ultra low power. And there are some, as I will explain, some sleep modes available in Wi-Fi you can use. But you cannot, like in narrowband IoT, tell the device now go to sleep for, let's say, 40 minutes or something like this. It's not really made for this. On the other hand, on Wi-Fi, you can easily set up a device where you program the device just to wake up once a day and then send data, which is extremely power saving and not using LTE. So for a sensor, yes, you could use something like Wi-Fi, but then we run into the problems of the high frequencies. So we use for our sensor networks typically the 868 megahertz, and then you can sleep for 10 days if you want, and then send something. And you hope that your data reaches the receiver. There are certain protocols for that. LTE is indeed a more controlled scenario where the base station can tell the devices sleep modes and controls more. So Wi-Fi, also LoRa, Sigfox, and these technologies, they're simpler in their settings. Typically cannot guarantee anything. So LTE can also guarantee certain parameters for narrowband, and that's a problem for all the other technologies that operate on the ISM bands. So if there's interference, etc., you run into problems. And narrowband LTE operates on licensed bands, so you will not have interference from other applications. So this is one of the difference. But if you really want to save power and you have only very few data and reliability is not the main point, then LTE is not the way to go. Then LoRa, for example, is much better. Or you can use, there's even a low power wireless LAN standard, but I'm not aware of any devices using this. But so most people for sensor networks for longer ranges go for LoRa. So this long radio technology. This is, it's different from LTE. So when it comes to guarantees, interference, capacity, etc. So there are certain limitations for LoRa, but that's one of the technologies. So if you're interested in this, I will briefly cover this in the last section. It's called LoRa, long range. Also LoRa Advanced are then the networks. There's a network running here in Berlin, and we are also contributing to this. So it depends on the technology. So there's not a clear winner. So it depends on technology and the application you want to use it for. Okay, some more questions. So the next sections will cover wireless LANs. So I will go through the classical standard 802.11 and up to the current devices. These are, the former name was .11ac, the so-called Wi-Fi 5 devices. So how all this works, just to give you, okay, to make the comparison between LTE as this more controlled system operated by large organizations compared to wireless LAN, well operated by you and me, so that you can compare these technologies. So please to have a look into these videos of wireless LAN technology. So are there more LTE questions? And for sure you can also come up in all the Q&A sessions or emails if you have any more questions, and I hope I can answer them. Okay, if there are no more questions. Okay, so thanks a lot to you all, and hear you next week. See you, read you, then we talk about wireless LAN. All the best, till next week. Bye.